On August 7, 1942, a substantial force of 16,000 United States Marines embarked upon a harrowing landing, wading through water that reached their chests, onto an island whose name, Guadalcanal, proved challenging for many to pronounce. This particular piece of land, a sweltering expanse of dense jungle nestled within the Solomon Islands archipelago, presented the Marines with a seemingly straightforward objective: to seize an airfield that Japanese forces were in the process of constructing. Remarkably, they accomplished this primary mission within approximately 36 hours, encountering surprisingly minimal resistance from the enemy. Following this swift takeover, the Japanese troops retreated into the surrounding jungle, leading many to believe the mission was successfully concluded. However, this initial perception proved to be profoundly mistaken, as the true ordeal was only just beginning to unfold. The captured airfield, it quickly became apparent, was far from complete. It was little more than a rudimentary strip of cleared earth. This was no ordinary terrain, but rather tropical soil that alternated between being intensely baked by the relentless equatorial sun and thoroughly saturated by torrential monsoon rains. When dry, its surface was as unyielding as concrete. Yet, with the onset of precipitation, it transformed into a viscous substance resembling thick chocolate pudding. Confronted with this challenging ground, the Marines swiftly grasped that they were facing an existential threat. A crucial, often overlooked, aspect of island warfare in the Pacific is that victory is not secured merely by occupying territory, but by asserting dominance over the airspace above it. This aerial supremacy, in turn, is utterly dependent on the functionality of a reliable runway. The Japanese command was acutely aware of the strategic asset they had forfeited. Within a mere few days, their bomber squadrons commenced a relentless assault on Henderson Field, as the Marines had christened it in honor of a pilot who perished heroically at the Battle of Midway. Nevertheless, the most formidable adversary was not the explosive ordnance raining down from above, but rather the ubiquitous mud. Subsequent to each downpour, the runway became utterly impassable. The Wildcats and dauntless dive bombers, which constituted the Marines' sole aerial protection, began to sink precariously into the saturated ground. Mechanics watched with mounting dread as the struts of landing gear vanished into the deep mire. In one particularly alarming incident, a pilot attempting to launch for an intercept mission found his aircraft's wheels carving trenches 4 feet deep before the plane had even achieved forward momentum. He was unable to become airborne, and consequently, the Japanese bombers he was tasked with intercepting arrived unhindered a mere 20 minutes later. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Engineers on the ground exhausted every known method in their attempts to stabilize the runway. They endeavored to fortify the surface by compacting it with crushed coral gathered from the adjacent beach, only to witness it completely erode during the subsequent torrential downpour. They then resorted to laying down sheets of pierced steel planking, repurposed from bridge-building supplies, but these metal sections buckled and warped under the intense tropical heat. Attempts to compact the soil using heavy rollers proved equally futile, as the rollers themselves became hopelessly mired. By the middle of August, Henderson Field's operational capacity was severely limited, functional perhaps only 3 days out of 7. On the days when the runway was unusable, the Marines on the ground were left utterly exposed. A lack of air cover meant that Japanese naval vessels could shell their positions with impunity, and enemy troops could be resupplied and reinforced under the cloak of darkness. The strategic calculus was stark and uncompromising. Without an all-weather functional runway, Guadalcanal was destined to fall. Should Guadalcanal be lost, the entire Allied offensive in the Pacific would face a debilitating stall, potentially for a year or even longer. Back in Washington, this critical dilemma found its way to the desk of the Army Corps of Engineers. They were receiving increasingly desperate radio dispatches from the Pacific Theater, all conveying the same urgent plea. "We require an immediate solution, and it was needed yesterday." The Corps of Engineers, however, was not starting their efforts from scratch. They had been grappling with the persistent problem of constructing runways on soft ground since before the attack on Pearl Harbor, conducting extensive tests at airfields spanning from the marshlands of Louisiana to the frozen tundras of Alaska. Yet, every single experimental approach they had undertaken had, in one manner or another, ultimately failed. And now, they were witnessing these very failures manifest in real time, thousands of miles away in the Pacific. The initial serious endeavor to address this issue occurred in early 1941, when engineers experimented with a material known as square mesh track. This innovative concept involved a grid constructed from welded steel bars, bearing a resemblance to a reinforced chain-link fence crafted from rebar. The underlying theoretical principle was sound: to establish a rigid framework capable of distributing concentrated weight across a broader surface area. They deployed this mesh at Langley Field in Virginia, then proceeded to roll a B-17 bomber, a formidable aircraft weighing 30 tons, across its surface. The mesh, however, collapsed and folded under the immense pressure, much like aluminum foil. It became evident that the steel was insufficiently thick to withstand the intense, localized force exerted by the aircraft's landing gear. Conversely, increasing the thickness of the steel to the necessary degree would render the mesh so excessively heavy that an entire cargo ship would be required simply to transport enough material for a single runway. Following this, the Hessian mat experiments were conducted in the spring of 1941. British engineers had previously reported some measure of success utilizing burlap fabric, coated in asphalt, as a temporary roadway material in the North African theater. American engineers, observing this, posited that if it proved effective for vehicular traffic, it might also serve for aircraft. Consequently, thousands of yards of heavy jute fabric were thoroughly saturated in hot asphalt, then laid across a stretch of soft ground at Wright Field in Ohio. Landing tests were subsequently performed using P-40 fighters. The initial landing proceeded without incident. However, the second landing resulted in the formation of discernible ruts. By the 10th landing, the fabric had completely disintegrated, and fragments of asphalt-soaked burlap were causing significant blockages within the landing gear mechanisms. By June, the entire concept was relegated to the rejection pile. The approach involving coral and gravel initially appeared to hold greater promise, primarily because it mimicked the natural characteristics of hardpan surfaces. In July 1941, engineers constructed test runways utilizing a composite of crushed coral aggregate blended with volcanic rock, materials that were readily available on many Pacific islands. This mixture was then compacted with steamrollers until it achieved a hardness comparable to concrete. For a period of 3 weeks, the surface demonstrated remarkable resilience, holding up perfectly under continuous aircraft operations. Then, the inevitable rain arrived. It was not a mere sprinkle, but a quintessential tropical deluge, depositing 6 inches of water in just 2 hours. The meticulously graded runway surface transformed entirely into a fluid slurry. Engineers observed in dismay as deep gullies, large enough to conceal a man, formed across the runway. Compounding the problem, once coral becomes wet and begins to decompose, it becomes nearly impossible to recompact, effectively necessitating a complete reconstruction of the surface. Pierced steel planking, widely known as PSP, came closer to offering a viable solution than any other material. Originally developed by British engineers, For the rapid construction of roads, PSP consisted of flat steel plates, each approximately 10 feet in length and 15 inches in width, perforated with numerous holes designed to reduce weight and enhance traction. The United States military initiated testing of PSP for runway applications in August 1941 at Bolling Field. Engineers were particularly impressed by the speed of its installation. A runway could essentially be shingled in a matter of days rather than weeks. However, PSP harbored a critical flaw when subjected to tropical heat. Steel naturally expands when heated, and under the intense equatorial sun, these plates would buckle and warp, creating hazardous ridges capable of shearing off aircraft landing gear. Pilots reported that landing on a warped PSP runway was akin to touching down on a washboard at a speed of 80 miles per hour. By the autumn of 1941, the engineering teams were rapidly exhausting their inventory of ideas and, more critically, their available time. The events of December 1941 dramatically altered the global landscape. Pearl Harbor was not merely a devastating military setback. It served as an urgent wake-up call, underscoring that the Pacific theater would necessitate innovative solutions that had not yet been conceived. The Corps of Engineers issued an urgent contract request to American steel manufacturers, outlining stringent requirements. We require a runway surface that can be installed within days, capable of supporting aircraft weighing up to 50,000 pounds, performing equally well in both mud and coral, and resilient enough to withstand tropical conditions without warping. Furthermore, it must be sufficiently lightweight to be transported across an ocean on cargo vessels already overburdened with tanks and ammunition. Carnegie Illinois Steel Corporation, based in Pittsburgh, accepted the challenging contract. Their lead engineer, James Marston, meticulously reviewed all the previous failures and came to a profound realization. Everyone had been approaching the problem from the wrong perspective. The prevailing strategy had been to attempt to create a surface that mimicked the properties of concrete or compacted earth. Marston's insight was considerably simpler and more elegant. Rather than attempting to combat the mud, one should instead endeavor to float above it. He began to conceptualize a design that bore less resemblance to a conventional road surface and more to a flexible, metallic carpet. By February 1942, Marston's dedicated team had successfully produced a functional prototype. This innovative design consisted of a steel plank precisely 10 feet long and 15 inches wide, yet every other characteristic of it represented a revolutionary departure from existing solutions. Firstly, its thickness, 3/16 of an inch of high-strength steel. This specific gauge proved robust enough to resist buckling under significant load, while simultaneously being thin enough that each individual plank weighed only 66 pounds. This weight was manageable enough for 2 men to maneuver it into position without the aid of heavy machinery. The engineers meticulously punched rows of holes across the entire surface, creating a pattern that strikingly resembled an industrial cheese grater. These perforations were not merely aesthetic. Each hole served a crucial triple purpose. It reduced the overall weight of the plank by approximately 30%, allowed water to drain through instead of accumulating on the surface, and created numerous edges that provided aircraft tires with enhanced grip. However, the true stroke of genius lay in the design of the edges. Both of the longer sides of each plank featured intricate interlocking mechanisms that Marston's team had spent months perfecting through rigorous iteration. One edge was designed with a raised lip culminating in a hooked end that curved distinctly upward. The opposing edge possessed a corresponding channel, precisely engineered to receive this hook. When 2 planks were laid side by side, the hook from one slid securely into the channel of the other, creating a robust lock. This connection was achieved not through bolts or welds, but purely through mechanical pressure. The resulting joint was sufficiently strong to withstand the passage of a 50,000-pound aircraft without the planks separating, yet it retained enough flexibility to allow the entire mat to bend and conform to uneven ground contours without fracturing. The shorter ends of each plank incorporated a different, simpler interlocking system, a straightforward overlapping joint where the end of one plank slid neatly beneath the next. This clever design created a continuous surface along the entire length of the runway, devoid of any gaps wide enough to snag an aircraft wheel. Furthermore, this overlapping mechanism ensured that as weight was applied, the planks actually locked together more tightly, rather than spreading apart. I am from the United States, and I find the video topic incredibly compelling. It highlights a critical, often overlooked aspect of military history, the logistical and engineering challenges that underpin major campaigns. It's fascinating how a seemingly simple problem, like a muddy runway, could have such profound strategic implications, potentially altering the course of the Pacific War. This narrative underscores the ingenuity and perseverance required to overcome seemingly insurmountable obstacles during wartime. Instead of succumbing to ground instability and spreading apart, the military conducted crucial evaluations in March 1942 at Camp Claiborne, Louisiana, a site specifically selected for its notoriously pliable soil, which closely mimicked the challenging conditions of Pacific mud. Engineers meticulously laid out 1,200 square feet of Marston's innovative interlocking planks directly onto this unprepared, swampy terrain. A fully loaded B-17 bomber was then maneuvered across the surface. The mat visibly flexed and rippled under the immense weight, yet steadfastly maintained its structural integrity. Over 3 consecutive days, a demanding regimen of 50 takeoffs and landings was executed. While some superficial scratches appeared, not a single structural failure occurred. Upon lifting a section for subterranean inspection, it was observed that the ground had compressed approximately 2 inches, but the ingenious interlocking system had ensured this compression was uniformly distributed, preventing any stress fractures or separation at the seams. Consequently, the military promptly placed an order for an astounding 60 million square feet of the material. To truly grasp the efficacy of these mats, one must delve into the physics governing the interaction between a colossal 30-ton bomber and soft ground upon landing. The fundamental challenge is not merely the aggregate mass of the aircraft, but rather the intense concentration of that weight. Consider a B-25 Mitchell bomber, which, when fully loaded, tips the scales at around 35,000 pounds. This entire load is channeled through its 2 primary landing gear struts and a single tail wheel. Each main gear is equipped with 2 tires, effectively funneling 35,000 pounds onto a minuscule contact area of roughly 4 square feet. This translates to an astonishing pressure of nearly 9,000 pounds per square foot impacting the ground with every touchdown. In stark contrast, soft soil typically possesses a bearing capacity of only about 300 pounds per square foot before it begins to yield and deform. The magnitude of this engineering dilemma is evident without recourse to intricate mathematical calculations. Marston mat brilliantly surmounts this challenge by artfully distributing the load across a multitude of interconnected planks. When an aircraft's landing gear wheel makes contact with a single plank, that individual plank does not bear the burden in isolation. The sophisticated system of interlocking hooks and channels ensures an instantaneous transmission of force to its 4 immediate neighbors, 2 positioned laterally, and 1 each in front and behind. These planks, in turn, disseminate the load to their own surrounding neighbors, creating a cascading effect of pressure diffusion. By the time the initial 9,000 pounds per square foot reaches the underlying ground, it has been effectively spread across an approximate 100 square feet of the mat's surface. As a result, the ground beneath now experiences a significantly reduced pressure of merely 90 pounds per square foot, a figure comfortably within the load-bearing capacity of even the most unforgiving soil. Crucially, the system's inherent flexibility proves to be every bit as vital as its demonstrable strength. We invite you to stay with us until the very end of this video. We would be immensely grateful for your kind like and subscription. Please also consider leaving a comment below, sharing where you are from, and your thoughts on this fascinating topic. Traditional concrete runways, by their very nature, are rigid structures, performing impeccably on stable, solid foundations. However, this rigidity becomes a catastrophic liability when confronted with soft, yielding ground. Should even a small section of a concrete slab settle or sink marginally below the adjacent areas, the inflexible material inevitably cracks. Once compromised, water infiltrates these fissures, initiating a rapid and widespread deterioration of the entire structure. Marston mat, conversely, avoids cracking precisely because it does not endeavor to be rigid. Each individual plank is engineered to permit minute, independent movements, mere fractions of an inch, while steadfastly maintaining its secure interlocking connection. The entirety of the runway surface thus effectively floats upon the ground, much like a colossal steel raft, gracefully conforming to any underlying settling or shifting without succumbing to fragmentation. The strategically punched holes found in each plank serve a purpose far beyond simply reducing the material's weight. They ingeniously create what engineers term a semi-permeable surface. In environments prone to heavy rainfall, such as the Pacific Theater where precipitation is incessant, these perforations prevent water from accumulating on the runway surface, which would otherwise create treacherous hydroplaning hazards for aircraft. Instead, water efficiently drains directly through the holes. The brilliance of this design lies in its specific dimensions. The holes are approximately 2 inches in diameter, ensuring that the much wider tires of aircraft still encounter an abundance of solid steel for optimal grip. Essentially, the tire perceives a continuous, solid surface, while water is presented with an effective drainage system. Trials conducted at Airfields in April 1942 conclusively demonstrated that water cleared from a Marston mat runway 6 times faster than from conventional solid surfaces. The innovative interlocking edges also yielded an unanticipated benefit: streamlined bomb damage repair. When an enemy bomber inflicted a crater upon a Marston mat runway, a simple patch, as one might apply to concrete, was not an option. Instead, entire sections necessitated replacement. Yet, because the planks interlocked without the need for welding or bolting, repair crews possessed the remarkable ability to swiftly unlock the damaged planks, slide them out, and seamlessly drop new ones into their place. At Henderson Field, engineers meticulously timed this procedure. A bomb crater that had devastated a 20-foot segment of runway could be fully repaired and rendered operational once more in under 40 minutes. This timeframe specifically refers to the replacement of the mat surface, excluding the task of filling the crater itself. Contrast this with concrete, where a comparable repair might consume several days and demand specialized equipment for pouring and curing new material. The inherent simplicity of the Marston mat system significantly minimized training requirements. Specialized engineers were not indispensable for its installation, only personnel capable of following a pattern and working with expeditious efficiency. On August 17, 1942, at Henderson Field, the inaugural consignment of Marston mat reached Guadalcanal aboard cargo vessels that had braved a perilous gauntlet of Japanese submarines to deliver their vital payload. Personnel from the Naval Construction Battalion, famously known as the Seabees, undertook the arduous task of unloading 36 tons of steel planking onto the beach, all while Japanese Zero fighters relentlessly strafed the shoreline. Their endeavor was driven by a deadline not measured in days, but in the precious hours ticking away before the inevitable arrival of the next Japanese bombing raid. The Seabees, largely unfamiliar with this novel material, were predominantly civilian construction workers, carpenters, steelworkers, and equipment operators who had been pulled from their peacetime occupations building highways and bridges across America just months prior. Now, they found themselves thrust into an active combat zone, grappling with the immense challenge of assembling a functional runway from scratch, all while under active enemy fire. The initial realization for these dedicated workers was that while 66 pounds per plank sounded manageable in theory, the reality of manually hauling those planks hundreds of yards in oppressive 100-degree heat and 90% humidity was an entirely different ordeal. Out of sheer necessity, they rapidly developed an efficient rhythm. Two-man teams would retrieve planks from the stockpiles and transport them to the edge of the nascent runway. A third individual served as a guide, meticulously positioning each plank to ensure the precise alignment of its interlocking edges. The first row of planks was laid with relative ease, simply placed side by side on the cleared ground. However, every subsequent row demanded the precise engagement of the hook and channel connection. The technique they ingeniously devised involved tilting the new plank at a slight angle, sliding its hook beneath the channel of the already positioned plank, and then dropping it flat. When a plank seated correctly, it produced a distinct metallic click, a sound that quickly became the most profoundly satisfying auditory signal these men experienced, signifying a successful and secure lock. The construction efforts unfolded in frantic, intense bursts, punctuated by relentless air raids. After this critical safety period, they would return to the runway, resuming their work precisely where they had left off. If a bomb struck a section they had already completed, they would promptly unlock and replace the damaged planks. If the impact occurred in an area yet to be covered, they would swiftly fill the crater with coral and continue laying the mat directly over it. By August 20th, a mere 3 days after the initial mat shipment arrived, a critical section of runway, measuring 200 feet long and 75 feet wide, was declared operational. While not a complete runway, Henderson Field would ultimately require a substantial 5,000 feet to safely accommodate bombers. This segment was entirely sufficient for fighter aircraft. That very afternoon, 19 Wildcat fighters and 12 Dauntless dive bombers, deploying from the carrier Enterprise, flew in. These aircraft, designated VMF-223 and VMSB-232, formed the legendary Cactus Air Force, a moniker derived from Guadalcanal's radio call sign. They were landing on a surface that, astonishingly, had not existed just 72 hours prior. Pilots reported a distinct sensation when landing on Marston mat compared to concrete or compacted earth. They noted a slight give, a noticeable flex that could be felt through the landing gear, with some describing it as akin to landing on a firm trampoline. This inherent flexibility proved to be more forgiving. Aircraft making harder-than-ideal touchdowns did not experience as violent a bounce because the mat effectively absorbed a portion of the impact energy. By September 5, 1942, Henderson Field boasted a fully completed Marston mat runway, stretching an impressive 5,200 feet in length and 150 feet in width. The entire installation process, remarkably, took only 19 days, even with persistent delays caused by enemy air raids and artillery fire. In stark contrast, traditional concrete construction methods would have demanded a minimum of 3 months under ideal conditions, a luxury that was utterly non-existent on Guadalcanal. While Guadalcanal unequivocally proved the fundamental concept, it was the subsequent developments that truly unveiled the profound strategic value inherent in portable runway systems. By early 1943, the United States military was meticulously charting an ambitious island-hopping campaign across the vast expanse of the Pacific, an offensive that would ultimately span 7,000 miles from the Solomon Islands to the Japanese home islands. A critical prerequisite for every single one of these captured islands was the rapid establishment of an operational airfield. The Japanese defensive strategy heavily relied upon transforming each island into an impregnable fortress, a process designed to prolong capture into months. Marston Mat, however, fundamentally disrupted and collapsed this timeline. In February 1943, during operations in the Russell Islands, the Marines landed fully anticipating fierce resistance, only to discover that the Japanese forces had already evacuated. Within an astonishing 60 hours of the first troops hitting the beach, the tireless Seabees had successfully laid a fully operational fighter strip utilizing Marston Mat. The sheer speed of this accomplishment was so astounding that when Admiral William Halsey arrived to inspect it, he famously inquired of the battalion commander if construction had commenced prior to the island being fully secured. The answer was no. The Seabees had simply attained an unprecedented level of efficiency. The swiftly completed Russell Islands airfield immediately provided crucial air cover for the subsequent strategic leap up the Solomon chain, thereby dramatically reducing what would have been weeks of vulnerability to a mere matter of days. The vulnerability of newly seized territories, once measured in lengthy construction periods, was dramatically reduced to mere days. Consider the intense situation at Munda Point on New Georgia Island in August 1943. This particular engagement presented a formidable challenge, as Japanese forces remained entrenched, deeply dug into fortified bunkers that commanded an impressive view over the prospective airfield location. Undeterred, the Seabees, renowned for their engineering prowess, commenced the arduous task of laying Marston Mat directly under the relentless barrage of enemy fire. In response to these perilous conditions, they devised and implemented audacious tactics that, on paper, appeared utterly suicidal yet, through sheer determination and coordination, proved remarkably effective. One half of the battalion courageously positioned the interlocking steel planks, while their comrades in the other half valiantly provided ceaseless covering fire with their rifles and machine guns. The cost of such bravery was indeed significant, tragically accounting for the lives of 14 men and leaving 47 wounded. Nevertheless, with an almost unbelievable speed, the vital runway was declared operational in a mere 11 days. Remarkably, Marine Corsair fighters began launching their critical missions from Munda even as Japanese snipers were still being systematically cleared from the surrounding perimeter, a testament to the urgency and innovative spirit of the forces involved. Moving forward to November 1943, the strategic island of Bougainville witnessed a pivotal evolution in military engineering practices, marking the nascent stages of experimentation with prefabrication techniques. Rather than the painstaking process of individually laying each plank, engineers stationed in Australia ingeniously began pre-assembling substantial sections of Marston Mat into formidable panels, each measuring an impressive 50 feet by 15 feet. These colossal sections were then carefully loaded onto LSTs, or landing ship, tank vessels, and transported across vast distances, arriving at their destination fully intact. Upon the LSTs, making their critical beach landings at Bougainville, powerful cranes were employed to meticulously lift these pre-assembled sections directly onto ground that had been swiftly prepared. This innovative method drastically cut down installation time. A runway that would traditionally have demanded 2 weeks of labor, plank by plank, was now completed in an astonishing 4 days. By December of that same year, Bougainville boasted 3 complete Marston mat runways, strategically arranged in a triangular pattern, an ingenious design that facilitated simultaneous takeoffs and landings, irrespective of prevailing wind directions, thereby maximizing air superiority. The sheer scale of Marston mat production figures eloquently underscores the central and indispensable role this groundbreaking technology assumed throughout the conflict. In 1942, a consortium comprising Carnegie, Illinois, and 9 other prominent steel manufacturers collectively churned out an impressive 8 million square feet of the matting. The following year, 1943, witnessed an exponential surge, with production soaring to an astounding 40 million square feet. By 1944, the annual output had reached a staggering 60 million square feet, a quantity so vast it was hypothetically sufficient to construct a continuous runway stretching from New York all the way to Philadelphia, if laid end to end. The military's insatiable demand for Marston mat was so immense that it inadvertently triggered a significant steel shortage, impacting other crucial wartime programs. For instance, tank production experienced a temporary reduction, as the nation's vital steel furnaces were strategically prioritized for the urgent manufacturing of runway matting. This critical period then led to January 1945, and the pivotal operations at Lingayen Gulf in the Philippines. We trust you are finding this account compelling. Please stay with us and watch the end of the video for the full story. We would be truly grateful for your like and subscription. We also invite you to share a comment below, letting us know where you are from and what your thoughts are on this fascinating topic. At Lingayen Gulf, the Marston mat was deployed in a manner entirely unforeseen and unintended by its original designers. Here, engineers ingeniously repurposed the matting, laying it across expansive sandy beaches to rapidly construct instant piers and robust roadways specifically for the passage of crucial supply trucks. It was swiftly discovered that the mat's inherent design worked just as effectively for distributing the heavy loads of wheeled vehicles as it did for the substantial weight of aircraft. Consequently, vital supply convoys, which would ordinarily become hopelessly mired and bogged down in the soft beach sand, could now drive directly and efficiently from their landing craft straight to the designated supply dumps located further inland, revolutionizing logistical operations. February 1945 brought forth the brutal and iconic Battle of Iwo Jima, an engagement that likely saw the most famous Marston mat installation of the entire war, despite its general lack of recognition by the public. The unique geological composition of Iwo Jima, characterized by volcanic ash so incredibly fine and loose, presented an unprecedented challenge, akin to attempting construction on powdered sugar. Traditional concrete could not cure properly, as the ubiquitous ash inevitably contaminated the mix. Compacted earth, a standard construction method, was simply an impossibility because there was no earth, only this pervasive, problematic ash. In this extreme environment, Marston mat emerged as the sole viable option. Engineers courageously laid the mat across all 3 airfields on the island, performing this perilous work even as the ferocious battle for Mount Suribachi continued to rage, a testament to its critical importance and the unwavering resolve of those who deployed it. Following the cessation of hostilities in August 1945, military planners largely presumed that Marston mat would swiftly become obsolete within a matter of months. The advent of peacetime heralded an era where ample time would be available for the meticulous construction of permanent, robust concrete runways. Consequently, vast quantities of the steel matting were stockpiled at various depots scattered across the Pacific, thousands of tons sitting idle in warehouses, awaiting eventual scrapping or sale. However, fate intervened on June 25, 1950, when North Korea launched its invasion of South Korea. Suddenly, the United States military found itself in an urgent scramble to establish air superiority in a theater of operations where critical infrastructure was virtually non-existent. Those previously forgotten stockpiles of Marston mat were hastily retrieved from storage. The Korean peninsula's terrain presented a stark contrast to the tropical islands of the Pacific. It was mountainous, subjected to brutal winters, and its soil frequently froze solid. Engineers grappled with significant doubts, questioning whether a mat designed for the humid, soft ground of tropical jungles could possibly function effectively in sub-zero temperatures. Their concerns were quickly put to rest. While steel undeniably becomes more brittle in extreme cold, the mat's ingenious interlocking design astonishingly maintained its integrity. The very flexibility that had enabled the mat to perform so well on soft, yielding ground proved equally effective on frozen terrain. As the soil froze and expanded, the mat gracefully flexed upward. Conversely, when it thawed and contracted, the mat settled back down, exhibiting no signs of cracking or separation. Kimpo Airfield, situated near Seoul, rapidly became the definitive test case for this remarkable adaptability. By September 1950, Kimpo Airfield lay in ruins, its concrete runways deliberately destroyed by retreating North Korean forces. Undeterred, U.S. Air Force engineers swiftly deployed Marston mat directly over the shattered concrete, achieving the extraordinary feat of creating an operational runway in an astonishing 72 hours. With incredible speed, F-86 Sabres began launching critical combat missions from Kimpo, even as concrete repair crews were still laboriously jackhammering rubble on adjacent sections of the airfield. The Korean War ultimately saw Marston mat utilized at 38 different airfields, and during this conflict, the military began referring to it by a new designation, PSP, or pierced steel planking. While the familiar name Marston mat gradually receded from official usage, the underlying technology remained fundamentally identical, a testament to its enduring design. In 1965, during the escalating conflict in Vietnam, the resilient mat reappeared, now nearly a quarter-century old. Astonishingly, some of the very same steel planks that had seen service on Guadalcanal were still fully functional after more than 2 decades. Engineers deployed it at critical locations such as Da Nang and Bien Hoa, establishing essential dispersal pads for helicopters and expanding existing runways. The Vietnamese climate, characterized by intense monsoons, extreme heat, and acidic soil, bore an almost uncanny resemblance to the Pacific Islands, where the mat was originally conceived and designed to operate. Consequently, it performed with the same unwavering reliability and effectiveness as it had in 1942, proving its timeless utility. However, it is at this juncture that the story of Marston mat takes an utterly unexpected and fascinating turn. Following the conclusion of the Vietnam War, this versatile material began to find its way into an array of civilian applications. Oil companies, for instance, started adopting it extensively in the challenging environments of Alaska and Canada. There, it was used to construct temporary roads and drilling pads across fragile permafrost landscapes, crucially without causing irreparable damage to the delicate tundra ecosystem. The very same principles of weight distribution that had prevented heavy bombers from sinking into the treacherous Pacific mud now served to prevent massive trucks from melting the sensitive permafrost. Notably, even environmental groups lent their support to its use, precisely because of its removable nature. Once drilling operations were concluded, the mat could be efficiently retrieved, allowing the tundra to recover, a stark contrast to the permanent scarring left by traditional gravel roads. January 2010 witnessed a catastrophic magnitude 7.0 earthquake that devastated Port-au-Prince, Haiti. While the international airport's main runway remained miraculously intact, the surrounding infrastructure was utterly destroyed, creating immense bottlenecks that severely hampered the flow of critical relief flights. In response, the U.S. military swiftly airlifted pallets of Marston mat, a product they were, remarkably, still manufacturing, and deployed it across damaged taxiways and parking aprons. This rapid intervention meant that cargo planes laden with vital medical supplies and sustenance could now unload their precious cargo and taxi to temporary parking areas that had literally not existed just 48 hours earlier. Thus, a technology originally conceived and designed to wage war against the Japanese Empire was now, decades later, directly engaged in saving the lives of earthquake victims, highlighting its profound and unexpected humanitarian utility. Even today, modern military forces continue to maintain extensive stockpiles of this indispensable material. The U.S. Air Force now refers to it as AM2 matting, aluminum matting, version 2, reflecting a strategic shift from steel to lighter, more advanced aluminum alloys to reduce overall weight. Yet, the fundamental design remains instantly recognizable. The same distinctive interlocking edges, the familiar perforated surface, and the identical basic concept that Marston first sketched back in 1942. The British Royal Air Force also employs it, and NATO forces notably deployed it in Afghanistan to expand crucial parking areas at Bagram Airfield. It consistently appears in disaster zones after devastating typhoons, floods, and hurricanes, essentially anywhere there is an urgent need for instant infrastructure on ground that is either severely damaged or entirely unprepared. Furthermore, sections of the original Marston mats are still remarkably present in the world. They can be found repurposed as utilitarian walkways, durable bridge decking, and even as distinctive decorative fencing. On some remote Pacific islands, operational sections laid during the crucible of World War II continue to serve their purpose, albeit weathered and worn, yet still functional after an astonishing 80 years. While history books and documentaries often spotlight the glamorous narratives of tanks, planes, and ships as the primary instruments of victory, the profound reality is that wars are fundamentally won by the unseen infrastructure, the often uncelebrated logistics, the intricate supply chains, and the unparalleled ability to transform an otherwise worthless piece of ground into a fully functional military asset, with a speed that utterly defies enemy expectations. Marston mat, in its unassuming brilliance, fundamentally altered the equation of how the Pacific War could be fought, yet its pivotal role remains largely unknown to the general public. Before the advent of these transformative steel planks, the capture of a strategically important island necessitated a protracted commitment to months of extensive construction before that island could yield any tangible military utility. Forces would seize the ground, only to then endure a lengthy period of waiting, while engineers meticulously surveyed the terrain, graded the earth, poured concrete, and patiently awaited its complete curing. Throughout this entire, vulnerable interval, the newly captured island remained essentially an expensive piece of real estate, and the occupying forces were exposed to considerable risk. The Japanese military understood this strategic calculus perfectly. Their defensive strategy was meticulously predicated on the assumption that each captured island would take so long to render operational that American momentum would inevitably stall. They would dig in, compelling the invaders to pay a heavy price in blood for every yard gained, knowing that even after a victory, the Americans would be bogged down for months, attempting to make the ground functional. The very concept of island hopping was, in their estimation, inherently destined to be a slow, grinding process. Marston Matt, however, shattered the deeply ingrained assumption. Suddenly, American forces possessed the capability to land on an island and have operational aircraft launching from it within a mere week, and sometimes even within a matter of days. This revolutionary speed fundamentally reshaped the potential aggressiveness of the American advance. Islands that were previously considered strategic liabilities, precisely because they would demand an inordinate amount of time to develop, instantaneously became viable and attractive targets. The remarkable success of the Central Pacific Campaign, encompassing pivotal battles like Tarawa, Kwajalein, and Saipan, was intrinsically linked to the fact that captured islands could immediately provide critical support for the subsequent assault, rather than becoming costly pauses that dissipated momentum. The statistical evidence is stark and compelling. By the close of 1944, the U.S. military had engineered and constructed over 300 airfields throughout the vast Pacific theater. A staggering 220 of these utilized Marston Matt, either in part or entirely. Without this crucial technology, perhaps only a third of those airfields would have been built, and their construction would have consumed 3 times as much time. Such a scenario would have translated into a significantly reduced number of forward bases, necessitating far longer flight distances for vital bombers, and severely curtailing air coverage for crucial naval operations. Ultimately, the entire timeline of the Pacific War would have potentially shifted by months, perhaps even by a full year, underscoring the profound and often overlooked impact of this humble, yet revolutionary, steel planking. The strategic timelines of military operations frequently experience significant alterations, often shifting by many months, or even a full year, due to various factors. A compelling illustration of this phenomenon can be observed in the extensive bombing campaign waged against Japan during World War II. The formidable B-29 superfortress aircraft, instrumental in ultimately compelling Japanese surrender, primarily commenced their missions from the Marianas Archipelago, specifically the islands of Saipan, Tinian, and Guam. These crucial island territories were successfully captured in the summer of 1944. Remarkably, by November 1944, a mere 5 months subsequent to their acquisition, these very bases were already serving as launch pads for colossal aerial bombardments directed at Tokyo. Such an accelerated operational readiness was exclusively rendered possible because engineering units possessed the capability to rapidly deploy Marston Matt runways, robust enough to accommodate the heaviest bomber in the American military's formidable arsenal, within a remarkably brief span of weeks. Had conventional concrete construction methods been necessitated for these airfields, the initiation of these pivotal raids would have been deferred until mid-1945 at the absolute earliest, and delay that would have fundamentally reshaped the entire strategic calculus for the war's ultimate conclusion. This remarkable engineering feat encapsulates a more expansive lesson regarding the power of innovation when catalyzed by intense pressure. The industrial powerhouse, Carnegie, Illinois, did not conceive of an entirely novel, exotic material or pioneer a groundbreaking, revolutionary manufacturing methodology. Instead, their approach involved a meticulous examination of established steel fabrication practices, prompting them to pose more insightful and pertinent inquiries. These critical questions revolved around fundamental engineering paradoxes. How could intrinsic strength be achieved without sacrificing necessary flexibility? How could an object be endowed with lightness without succumbing to inherent fragility? And, crucially, how could a system, despite its underlying complexity, be rendered sufficiently straightforward for assembly by battle-weary personnel operating under the immediate threat of enemy fire, ensuring accuracy and reliability? The presenters of this historical account encourage their audience to remain engaged and watch the conclusion of this video. they would be immensely grateful for a like and a subscription. Furthermore, they invite viewers to share their geographical origin in the comments section and offer their insights on the compelling subject matter discussed. The inherent brilliance of the Marston math system resided squarely in its fundamental simplicity. Individual planks designed to seamlessly interlock, strategically placed perforations engineered to facilitate water drainage, and steel composition formulated to flex under stress without succumbing to fracture. While military historians frequently characterize the Pacific War as fundamentally an aircraft carrier war, a submarine war, or a conflict dominated by intricate logistics, all undeniably accurate assessments, it is imperative to recognize that underlying these narratives was a ceaseless conflict of engineering challenges surmounted against seemingly insurmountable deadlines. Marston and his dedicated team at Carnegie, Illinois likely contributed to the preservation of more human lives and expedited the conclusion of the war with greater efficacy than any singular weapon system. Their profound impact was not achieved through acts of destruction, but rather through ingenious acts of construction. They masterfully devised methods to transform treacherous mud into functional runways, dense jungles into operational air bases, and previously considered worthless islands into vital strategic launching platforms. In essence, they rendered the logistically impossible entirely feasible. And in the unforgiving theater of war, the mastery of logistics proves to be the ultimate determinant. These unassuming perforated steel planks, with their straightforward interlocking edges, did not merely serve to construct airstrips.